In this lesson, we're going to start digging deeper into how the Swift standard library actually works. We're going to learn that by making some small additions and adjustments to your custom types and collections, we can leverage a lot of power from the standard library itself. It's important to learn as early as possible how to structure our code around the standard library. The key to this is the standard library's family of protocols. We've already looked at some standard library types such as int, string, array, and set, but it's really the library's protocols that are the key to leveraging its power. As an experiment, I ran the above command on a Swift 4 release download folder to get an estimate on the number of protocols in the standard library. My experiment draws the following list of 62 protocols. In order to master Swift, it should be a goal to learn about most of these protocols. In this lesson, we're going to get started with a few simple protocols: CustomDebugStringConvertible, CustomStringConvertible, Comparable, Equatable, and Hashable. These are simple protocols that you can and should adopt to make your custom types more useful. After this, we'll take a look at the Expressible by family of protocols. This will lead us to an introduction on protocols with associated type. Okay, so let's try implementing CustomStringConvertible in a playground. I have the person type here again with the first name, the last name, and a computed full name property. I'm using a slightly different format here, which you'll see why a little bit later. So let's define a person, and let's print that person. As you can see, not a very user-friendly output. We're going to implement CustomStringConvertible to have some control over that. So I'm going to create an extension and implement CustomStringConvertible. Now if we look at the definition of CustomStringConvertible, you'll see there's just a single method here, var description string, and it's read-only. So I'm just going to implement that method. Now in the case of person, I already have this full name computed property, which I think is a reasonable textual string representation of the type. You could possibly show it in a user interface. So in description, I'm simply going to return full name. Now let's run the code again with our print statement. And you'll see this time print is making use of our custom description method from CustomStringConvertible. Okay, so let's implement CustomStringConvertible and CustomDebugStringConvertible in a playground. Here I have the person type as before, and I've created an instance P of a person. And the first protocol we're going to start with is CustomStringConvertible, so I'm going to implement that in an extension. Now if we jump to the definition of CustomStringConvertible, we'll see that there's just a single method here, var description, which is a string which is read-only. Now in the case of the person struct, we already have the full name property, full name computed property, which I think is a reasonable simple string representation of the person, which we might maybe use in a user interface. So I'm just going to implement the description method, and I'm simply going to return full name. Now when we print P, execute that code, we'll see in the debug area that we're actually calling the description method and therefore also the full name method when we print out an instance of P. Let's continue working with these protocols, this time CustomDebugStringConvertible. I'm going to change the print statement at the bottom here to dump. So currently we're printing the output of the description computed property from CustomStringConvertible. If I run that now, you'll notice that dump gives us on the first line the same value from description which we implemented in CustomStringConvertible, and we also get the values of the two properties. Now we're going to implement CustomDebugStringConvertible to have a bit more control over that output. So I'm going to add another extension adopting CustomDebugStringConvertible, and again let's have a look at the definition, and we have a single computed property here, debug description string. This is the method we're going to implement. So this time around I'd like to add a little bit more information to the output. So I'll start by just copying the full name property, and I'm going to add labels. To the output. Perhaps that'll be a little bit more useful when I'm working with the type. And if we run that code again, you'll see in the first line we have the output of our debug description. Alright, this time let's implement Equatable. We have our person type again, and I've created 3 instances here. P, Q, and I also have R, which has the same first name and last name as P. Now let's try using the Equatable operator with my instances, and as you'll see, we can't do that. First we need to implement the protocol. So let's add an extension person Equatable. And again, let's go and have a look at the definition of the protocol. Just a single method here. It's actually a static method, and here we can see the equality operator. Now for convenience, I'm going to copy that method and paste it in here. Now we can't use self here. We're going to have to change that to person because we're comparing 2 persons. And I have decided that I'm going to make the equality of a person based on the full name, because that's just a convenient, quick way to do it. So I'm simply going to return left-hand side dot full name equality right-hand side full name. And now if I uncomment my 2 examples at the bottom here and run that code, you'll see that P does not equal Q, but P does equal R. The next 2 protocols are a little more interesting. Equatable and Comparable add the ability to compare and check equality between your types. Equatable is almost always a good idea to adopt. It's really strange to want to use the equality operator on your own types. Comparable, on the other hand, may not always be appropriate. However, if your types could be stored in a sorted collection, then you will want to adopt Comparable. Okay, so now let's implement Equatable for our person type. I have 3 instances of people here, P, Q, and R. P and Q are different, but P and R have the same first name and last name. Now if we try to use the equality operator in the playground, we'll have an error that we can't use those operators with the person type. So we're going to implement the equality protocol in order to support that. So again, I'm going to create an extension person, and we're going to be adopting Equatable. And again, I'll look at the definition of the protocol, and you see we have a single static method which uses the equality operator. This is the first time we're looking at implementing an operator. For the sake of convenience, I'm going to copy that method, return to my extension, and notice that we have self here in the argument types which come from the interface of the protocol. When we implement the protocol method, we have to change that to the actual type we're working with. And for my person type, I've decided that I'm going to implement equality based on the full name computed property. That seems like a simple way to have a basic equality. So we're going to return left-hand side dot full name is equal to right-hand side dot full name. Just as simple as that. Now if I uncomment my examples at the bottom here and run that code, you can see the first result false, P does not equal Q, but the second result true, because P does equal R if we're matching on the full name computed property. Alright, let's finish the convenience protocols with comparable. I have the person implementation again here, and I'm including my CustomStringConvertible implementation and also my Equatable implementation from previously. You'll see why shortly. Again, P, Q, R instances of person. At the bottom here, I'm creating a array A, And in the final statement, I'm going to try sorting that array. And you'll see we get an error here, missing argument for parameter by in call. This is because Swift doesn't know how to sort our person types. So the only way we can do that at the moment is by specifying a closure. So I'm going to do that first. And I'm going to sort person types using the full name again. So the implementation, I just need to do left-hand side dot full name is less than right-hand side dot full name. If we run that code now, we'll get a sorted output. However, we're going to adopt comparable, which will allow us to do this much better. We won't have to specify a closure in order to sort the array anymore. So I'm going to add a new extension to person with the comparable protocol. Let's have a look at the definition. And at the start you can see already that the comparable protocol inherits from Equatable. So in order to implement comparable, we also need to implement the methods in Equatable. And we've already done that, so there's less work for us to do. There are quite a lot of methods in the protocol. But if you look at the top of the documentation, it says the top method, the less than operator, this function is the only requirement of the comparable protocol. So actually we only need to implement the less than method. So let's return to our version. So I'm going to replace the comparable implementation from before with comparable. So we already have one of the methods implemented here, and the second method we need is the left-hand side less than method. And again, I need to change from self to person, and I can actually copy the same implementation from the closure at the bottom. And there we've implemented comparable for person. Now because we've adopted the comparable protocol, we no longer need a closure in order to sort the array of our person instances. So I can actually delete this, run the code, and Swift will be able to use our comparable protocol implementation rather than the closure we previously needed. The final simple protocol we'll look at here is Hashable. Hashable is necessary for any type that you want to store in some form of hash table data structure. The two collections of this type that we've covered so far are set and as a key to a dictionary. It's important that we've covered Hashable last. Hashable and Equatable should always be considered together. The simple point is that if instances of a type are equal, then they should always have the same hash value. We'll look at this at more depth in a playground exercise. Alright, so let's adopt Hashable for our person type. I'm including our Equatable implementation here for quite an important reason. And I have 3 instances again of the person, and at the bottom here I'm going to try and put P, Q and R into a set. As you can see, again we have an error message here because we aren't implementing Hashable. So let's go ahead and implement Hashable. So again, I'm going to add an extension to person with Hashable, and let's look at the definition. So this time the only method we have is a computed variable hash value, which is the hash value of our type. Now calculating hash values is a complicated topic, but we're going to take a reasonably short way to do this in this implementation. So let's just return hash value. So the important point when implementing Hashable is that we should be relying on the same property or properties in the hash value as we should be relying on in Equatable. So in this case we're using full name, and fortunately strings already support Hashable in the standard library, so we simply need to return the full name of our person and its hash value. And let's run the code now, and as you can see we can put our person types into a set.